Hi everyone. So first I want to just begin by saying, thanks for showing up and watching videos, and I hope that everybody's being safe. But I'm sure that we're all ready for mathematics, so let's just jump on in, right? So first we're going to recall. If we have the position of a function is given by some function s of t, the position of some object is given by s of t. Remember that the velocity we usually say is v of t, and we can compute v of t by computing s prime of t. We also know, that's my cat, we also know that this is, in notation, the derivative with respect to t of s of t. And recall further that if our velocity function v of t is positive, that means that the object is moving, in the positive direction, whatever that is. It could be up, right? If it's vertical position, then positive velocity would be moving upward. If it's moving along the x-axis, then positive velocity would mean to the right. It just depends on the context, but it's moving in the positive direction, whatever that means on context. If v of t is less than 0, if it's negative, then the object is moving in the negative direction. So again, if it's moving up and down, negative velocity would imply that it's moving downward. If it's moving left to right, the negative velocity implies that it's moving to the left. And if v of t is 0, that implies that the object is at rest. Even if it's 0 for just a moment. Even if it's 0 for just a moment. And a quick diagram helps see that, right? Suppose that we graphed projectile motion, right? So here's t on the x-axis. Here is s of t on the y-axis there. And suppose that you say throw a rock straight upwards. And this is only moving in the y direction here. We know that for an instant, the rock reaches its maximum here, and it's stopped for a second. Or not a second, instant. It stopped for an instant. It goes up, 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 stops, and then it begins to fall. But for the instant that the velocity function is equal to 0 here, that particle has stopped. It has 0 velocity. All right, so with this, we have a new idea today. And that idea is called speed. The speed of an object at time t is given by the absolute value of the velocity function. Given by the absolute value of the velocity function. So what this means is that speed is the magnitude. If we had vectors, that would mean something different for us, but for our purposes, it just means the size, the distance from the origin, the size of the velocity. But notice that because we're taking the absolute value, it's always positive, right? So there's no direction. There's no positive or negative to indicate the direction in which the object is moving. So it does not give direction. As an example, let's consider a simple case. Suppose our velocity function v of t is t squared minus 4. Let's sketch this velocity function. Let's sketch this velocity function. I know we'll have x-intercepts at -2 and 2. And this point here is at t equals 0. What would the speed of this function, what would the graph of the speed look like? Pause the video, see if you can guess what you think the speed of this particle will look like. So if we wanted to graph the speed, we know that this is the absolute value of the velocity function, right? So to graph this, what do we want to do? We're really graphing the absolute value of t squared minus 4. The absolute value of t squared minus 4. We could break this into a piecewise function and graph it the old-fashioned way like we did in pre-calculus, but let's just be a little quick and easy here. What do we know the absolute value function does? We know that if it's positive, it keeps it positive. If it's positive, it keeps it positive. And what does it do if it's negative? It takes the negative of it. And what does multiplying by a negative do on the outside? That's your vertical flip. So it flips it about the x-axis. So here's what the absolute value function looks like. And this is now a graph of the speed of a particle with this velocity function v of t. Let's do another example. If the position of an object is given by s of t equals to cosine of 3t, find the speed of the object at time t equals pi divided by 4. Pause the video. Try to see if you can do this yourself. Okay, so to compute the speed, first and foremost, we need the velocity function, right? The velocity function is, of course, s prime of t. And to take the derivative of s of t, I know the derivative cosine is negative sine of 3t. Now we need chain rule to multiply by the derivative of what's inside, which is 3. And now for the speed at t equals pi divided by 4, we simply need to compute the absolute value of v of pi over 4, which is the absolute value of negative 3 times the sine of 3 times pi over 4. Easy, right? So now we know that the sine of 3 pi divided by 4 is the square root of 2 divided by 2. And the absolute value of negative 3 times the square root of 2 divided by 2 is just 3 square root of 2 divided by 2. No problem. All right. Let's give a new definition. An object is speeding up. What does it mean for an object to speed up? Oops, speeding. Speeding up if the speed is increasing, right? If our speed is getting larger and larger, then we say that our car, or whatever the object is in this case, is speeding up. An object is speeding up if the speed is increasing. And an object is slowing down if the speed is decreasing. So what does this mean? How can we look at this? Let's go back to the graph that we had in one of our previous examples today. Let's quickly graph the speed function where the velocity function was t squared minus 4. Let's graph this again. We know it looks something like this, right? This point here is 2. Here's negative 2, and this point is at t equals 0, right? So where is this, if a particle has this speed function, where is it speeding up? Pause the video, try to see if you can answer that question. So the object is speeding up if the speed is increasing. What feature of this graph do we look at if we want to see where it's increasing? We look at the slope of this graph, right? So if it's increasing, I need to know where the slope of this graph is positive. So let's make a little chart. If it's speeding up, I need to make sure that the slope of this graph is positive, and we'll revisit this idea in the next video. But just visually, we know that that's going to happen here. We have an increasing function, and that's on the interval from -2 to 0. And where else are we increasing? From 2 onward to infinity. Because my speed function is moving upward. It's an increasing function, right? And again, increasing, we can see that the slopes of the tangent lines are positive at every point on this curve, on these intervals. And where are we slowing down? We're slowing down where the speed is decreasing, right? So where is my speed function decreasing? We're decreasing from -infinity to -2. And then from 0 to 2. Cool. No big deal. All right. Let's talk about projectile motion. If you've taken physics, this will hopefully seem familiar. If not, that's totally cool. And we'll derive this formula whenever you take calculus 2. But for now, let's just state what an equation for projectile motion is. All right. Suppose a particle, or an object, if you like, has a position function. And it's only moving under the effects of Earth's gravity. So it's only moving now under the effects of Earth gravity, right? If you toss a baseball in the air, it's going to come down, not because you've done anything to it, but because the force that's acting on it is the gravitational force, right? And the position function, if you have an object moving only due to Earth's gravity, there's no resistance here due to wind or any other effects, is going to be given by S of t is 1/2 gt squared plus v naught t plus s naught, where g is equal to either -9.8, and it has units meter per second squared, or -32 feet per second squared, depending on the units. So in the problem, if you see meters, you're going to use -9.8. If you see feet, you will use -32. V naught in our position equation is the initial velocity, and S naught is the initial position. Just for fun, let's compute v of t. And if you've taken physics, this function will look hopefully familiar to you. V of t is s prime of t, of course. And so if we differentiate this function up here, well, what's g? G is a constant, right? V naught is also a constant, and S naught is also a constant. So the only variable is t. So to differentiate S, it's going to simply be g times t plus v naught. V equals v naught plus gt. I hope that that's a familiar formula if you've taken physics. And we'll revisit this in calculus 2 and derive everything and see where it comes from. So with that, let's work a problem and see how we can answer questions with projectile motion. All right. So let's read this together, and then I want you to pause the video and try to work this for yourself. Suppose you throw a rock upward off of a 100-foot building at 10 feet per second. What is the speed of the particle 2 seconds later? When is the particle speeding up? When is it slowing down? And what is the particle's velocity the instant that it hits the ground? Pause the video and try to work this yourself. Okay, so what do we know here? Let's make a chart of what we know. Because we need to first and foremost construct a position function. Before we talk about velocity and speed, and speeding up or slowing down, we need to know a position function so that we can start taking a derivative, right? So we know we throw it upward off of a 100-foot building. So a 100-foot building tells us the initial position. Our initial y position is 100 feet, right? What's our initial velocity for this particle, or this rock? Well, I've thrown it upward at 10 feet per second. So if it's upward, it's moving in the positive direction. So what's the sign, SIGN sign, of the velocity? It's positive, right? So it's positive 10. Let's just go ahead and look ahead to other problems that you'll certainly see. If we threw it downward, then we would instead have our V naught be negative 10 in this case if we threw it downward, because the SIGN sign tells you the direction. And then what's G? G is going to be negative 32. Oops. Feet per second squared. And with this, let's make our position function. We know that S of t is going to be equal to 1/2 of this number, so that's negative 16, t squared, plus 10t plus 100. And just as a note, my t's, I always have the loops on my t's, and my plus signs have no loops, and I hope that that helps increase the readability of this hot mess here. So let's start answering the questions. To do anything, we need the velocity, right? What's v of t? Well, it's negative, if we take the derivative, it's negative 32t plus 10 is our velocity function. So, part A. What's the speed 2 seconds later? Well, it's asking us to compute the absolute value of the velocity at time t equals 2, right? So this is the absolute value of negative 32 times 2 plus 10, which is positive 54, right? The absolute value gets rid of that negative. How do we do part B? When is the particle speeding up and when is it slowing down? Well, let's use the same trick that we did before. Let's graph our velocity function. I know that I'm going to have a negative slope with a y-intercept at 10, right? So let's graph it. And it makes seeing what the speed is even better. And graphing the speed is easy peasy. So on the x-axis I have t. On the y-axis I have my speed function, v of t. And it will look something like this. Yeah? And this is, I hope you see, the absolute value of negative 32t plus 10. But how do we answer the question, when is it speeding up, when is it slowing down? Remember, to speed up means that this speed is increasing. So when are we speeding up? We're speeding up where this is increasing. Well, what's this point here? This point is where negative 32, our velocity function, negative 32t plus 10, is equal to 0, which happens at t is equal to 10 divided by 32. Oops, that got off the screen there, didn't it? I'm sorry about that. There it goes. So we set our velocity function, negative 32t plus 10, equal to 0, and we solve for t to find the point at which this absolute value has its corner. So we know after that point we will have positive slope on this speed function. But does it go to infinity? Does it go to infinity? No, right? I mean, it's a rock that's falling off of a building, so we know that this function has a domain restriction, right? So where will it for what values of t is this function actually valid, right? How do we solve that? Well, we need to know where the rock hits the ground. We know that the rock hits the ground whenever s of t is equal to 0. So at what time does this happen? When does s of t equal to 0? Whenever you plug this in a calculator, you'll see that it is 2.832, I hope. And so we're going to be speeding up all the way until the instant that it touches the ground there. And when are we slowing down? When are we slowing down? We're slowing down from whenever we first toss the rock, right? As the rock rises, it gets lower and lower speed as it goes up, and then it stops and then starts accelerating downward. So we know that we're slowing down from the instant that the rock leaves our hand at time t equals 0 up until the time that it turns around, which was at 10 divided by 32. All right, and last part is part C, which asks what is the velocity whenever it hits the ground? Oops, let me fix my papers. What's the velocity whenever we hit the ground? It's asking for v, and what was the time at which we hit the ground? We already computed this, right? This was 2.832. And the velocity at that time, I hope, is negative 80.624. Alright guys, so that's all for this video. I'm going to post another one shortly on higher derivatives and acceleration and things. I hope that this helps. If you have any questions, please feel free to reach out via email. I'm happy to help via email, or we can set up a time to Zoom as well. So hope everybody enjoys this. If you have any comments, critiques, or concerns, feel free to reach out and let me know. Thanks so much.